Good morning, everybody. My name is Brent Peltola. I am the Executive Director of Partners in Research Canada, and I am pleased to be your host today for this Junior Astronaut live event with our guest, Amit Sidhu from Western University. Amit is going to talk about the evolution of cosmic carbon, and then we are going to talk about the Junior Astronauts Survivor Moon activity. So I'm going to turn this over to Amit to introduce herself a little bit more and then get into the presentation. Good morning, Amit.
Thank you, Brent. Thanks for the introduction. And good morning, everyone. As you know, my name is Amit, and I'm a PhD candidate in the University of Western Ontario in London. I did my undergrad and master's in physics. And that was not when I was interested. I wasn't pursuing astronomy as a full-time career then, but it was in my master's when I did a special course in astronomy and learned so many cool things, which I'll be sharing some of them with you today, that's when I decided to pursue it as a full-time career. And I started my PhD in 2017. Today I'll be talking about the astronaut campaign, and we'll do it together. So let's just dive in. I'll share my screen. Perfect. All right. So, okay. So when we look into the night sky, we look at stars, we see so many stars and an empty space between the stars. But in reality, the space between the stars is not empty, and that space is filled with some clouds of gas and dust, which we call as the interstellar medium. And that is what I study. So interstellar medium is nothing but the material between the stars. So it is made up of gas and dust. A majority of it is gas, 99% of gas, and just 1% dust. Gas is primarily hydrogen and some other elements, but mostly hydrogen. So on the right, there is a picture of such gas, such cloud of gas and dust called the Orion Nebula. It is in our galaxy, very close to us. It can be, the image that you see is in the visible wavelength. We cannot see with our naked eye because it's not very bright. But when we look with the powerful telescopes, we are able to see this cloud of gas and dust. As you can see, so this star, this nebula is powered by a star at the center, and that's what giving it the brightness. The red color that you see is because of the hydrogen in that cloud, and that is emitting in the red. So if you see a red color, that is because of the hydrogen in that cloud. Little bit of yellowish and green you also see in this nebula or cloud, and that is because of the oxygen. So there's this Orion Nebula is one such example of clouds of gas and dust, but there are millions of such gas clouds in our galaxy, which I study. So these clouds are important also because they are sort of breeding grounds for many molecules, complex molecules. So they're the molecules such as amino acids, which are building blocks for our life. We sort of think that they originated in space. So those molecules, we believe, they formed in such clouds of gas and dust. And we think that those molecules originally formed in space, but then at some point got spit out into the atmosphere and then got engulfed into some asteroids and comets. And those asteroids and comets, when hit the Earth, long back ago, 4 billion years ago, when they hit the Earth, those brought the amino acids to Earth, and that's how life started on the Earth. I think this is what we believe. So when we see the asteroids and comets, when we study those, we do find an evidence for the amino acids in there, which are building blocks for life. So this gives us a sort of an explanation that maybe that life really originated in the space. So it brings us to this question that we really have to test that, does life have an interstellar heritage? And if that is the case, are we alone? If that is the case, so is there other planets, or is there somewhere else in space where we can find amino acids, or we can see the life as we see on the Earth? So these are the questions that everyone in sort of that is somewhat driving the astronomy, and that we try to address. And to address these questions, we need to really understand how the molecules are forming, those molecules that we see are building blocks of life, how they are forming in space, what are the physical conditions, under what conditions they survive, and how they evolve into the complex life forms that we see. So that is where my research comes in. I study two complex molecules. They are large organic molecules. The organic molecules are those which have made up of carbon and hydrogen. So I study two of those large molecules that exist in space. One of them is polycyclic aromatic hydrocarbons. It's a bit of a long name, so we have just given a short name called PAHs or PHs. So I study those PAH molecules in space, and another kind of molecule that I study is a fullerene molecule. It's a soccer-shaped molecule entirely made up of carbon. And it's the most stable molecule that we see in the space, and I study these molecules. So what we have seen that these molecules are present everywhere in the universe. There's no place in our, they are present in our galaxy, they are present in other galaxies as well. So they're there, and because of these molecules being organic, they become important to study for the inventory of the life or the organic carbon. So, and the specialty of these molecules is that they're very sensitive to the location where those molecules are found. So, for example, this is another example of a gas, cloud of gas and dust. And you see that the green emission that you see here is coming from the fullerenes, the soccer ball molecules, and it's organized nice ring outside that cloud. The red emission that you see is just like a hoop shaped, is coming from the PAH molecules, and it's very closer to the star. And the blue emission is coming from a hot gas. So you can see that the full emission from the fullerene, or the light from those molecules, is not very randomly distributed in that cloud. It's very neatly organized in a ring. So that means that it is very sensitive to the physical conditions of that particular region, and it gives us a hint that in what condition, based on that light, it gives us a hint in what conditions we can see those molecules, in what conditions will those molecules survive, and how will they evolve. And it also gives us a hint about the geometry of the molecule. If we keep on studying many such clouds, we get an idea about the geometry of the cloud that we're looking at. We get an idea of their formation, how they formed, and how those molecules survive, and how they evolve, eventually how they get into the space and eventually come to the Earth. But this also has an additional advantage, that we can sort of build a space weather station, because of these molecules are very sensitive to the physical conditions of the region. So imagine that it's a station that we just look at the light coming from those molecules and say, okay, this is the light. If this much amount is light coming, we say this X is the temperature of that region, that it's not very hot, or if light is more, we'll say the temperature of that region is higher. So it's sort of it also can act as a space weather station if we study those molecules. And that's a building project that we, as people at NASA Ames, are also working on it, to use those molecules to sort of build a space weather station. And this brings me to the Junior Astronaut campaign that all of you, which are from the students, which are the younger generation, can contribute to the space science and astronomy, and build up and develop the science. So the Junior Astronaut campaign is initiated by the Canadian Space Agency. It's launched to inspire the young Canadian youth to get involved into the science and technology. So it's partly one of the main reasons for this campaign is the Canada is launching, is going to moon. It's part of the Lunar Gateway mission to the moon, which is in collaboration with the NASA. And so in the Lunar Gateway mission, we are sending an orbit, in a spacecraft to orbit the moon. And the Canada will be providing a Canada arm, which is just a robotic arm that will be used for to fix any problems in the spacecraft. So it's a robotic arm that will do that, and so that the Canadians become a young youth become aware of it, and that there will be astronauts on that spacecraft, so that people, the young youth, know that they have some opportunities that they can avail. So that for that we have the Junior Astronaut campaign, and the goal is to inspire the students about the science using the space, and so that we have to inform them about the space careers and that how they can become an astronaut or we can contribute into an astronomy. So the important thing that I want to address here is that you don't necessarily have to do just the physics or just chemistry or be an engineer to become an astronaut. You can come in, you can either be in biology, you can be in physics, chemistry, engineering, arts and sciences, and the policies making. You can be in any stream of that you are interested in and still contribute towards the space sciences and still become an astronaut. So that's what one of the mission of the Junior Astronaut mission of this campaign is, to make the people aware of the different space careers that they can pursue. And also to show them what roles they can play in the future missions to the moon, because now that there is a Lunar Gateway mission in which Canada is being part of, and because they will be sending astronauts there, so Canadian youth, which has a chance to be that astronaut who can go to the moon. So in that, there are important dates that I want you all to remember, that our registration is still going. And so there are activities that you have to complete. For the educators and organizations, will have to do at least one activity if they want to have, and once they have completed that activity, they can submit it, and they'll be in a draw, and they'll have a chance for some professional space scientist or an astronaut to visit your organization. And the students also have an opportunity, if they complete an activity in 3 streams. There are 3 streams in which they'll be doing activities. One is the science and technology, other one is the fitness and nutrition, and the third one is the teamwork. So these 3 activities, if the students are doing the complete activities in all of these 3 streams, they can also submit their work, and they'll have a chance to go to a space camp, which will be organized in Montreal. And with that, let's get to—
So, Amik, before we get into the junior astronauts, I was wondering, and I'll remind the classrooms that are on, if you have questions, please open your Q&A window and submit them, and I can relay those questions to Amik. But I had a couple that came through that I was hoping we could talk about. First of all, you talked about amino acids and other elements coming from space and populating the Earth millions of years ago. Does Earth continue to be hit by these elements? Are there new amino acids coming from space all the time?
So The asteroids and there's some bombardment like meteorites, they hit the earth. Yes, they do, but that is not the one that started life on the earth. Those were like bigger impacts when the earth formed 4 billion years ago. That's when the amino acids come. But yes, the meteorite samples that they collect now, which hit the earth, they do find an evidence of the amino acids in those samples as well.
Okay, and I wonder if you can talk a little bit more, maybe you can go back to the slide with the ring of colors. What organizes that, those elements in that ring? Are they held there through gravitational forces, or is there some other reason they're organized in that way?
That is exactly the point that we are trying to understand, that what are the different, what process is keeping the molecules there, as in we are not very completely sure of at this moment, but this is what we want to understand, that why do we see those molecules so nicely organized in a ring and not just randomly distributed everywhere. So that is what we are currently looking at. We do know that it wouldn't survive very closer to the star, but so we wouldn't find it in the hot region, like this very ionized gas, blue color, we wouldn't find there. We know that for sure, so that's why we don't see the green color there. But beyond that, why don't we see molecules just beyond that ring, and why in that particular ring is a question that we are addressing now.
All right. Okay, well, that's all the questions we had right now. So if we want to bump back forward to the Survivor Moon activity, that'd be great.
All right, so the Survivor Moon activity. All right, so for this activity, the students will have to organize in teams, and each team will be a crew member, or crew that will be going to space. So each crew member will be an astronaut. So you have to imagine a scenario that instead you are going on in a mission to Moon, but due to some emergency conditions, you are not able to land at the position where you were supposed to, but land 50 kilometers away from the outpost. So, and in your capsule, in your lunar capsule, you have 15 items that you can take with you for your walk to the 50-kilometer walk to your actual outpost where you wanted to land. And the activity would be your task would be to rank how the priority of those items, like what item would you rank as the highest priority that you have to take out of those 15 items, and what item would you think is not very useful and you would probably not take it with you. So you, in this scenario, you do have your space suits, but you'll have to carry some additional items with you so that you can survive that 50 kilometers walk. And you have to rank those as a team. So these are the 15 items. So it's a stellar map, a case of a dehydrated milk, magnetic compass, signal flare, a small fire extinguisher, a raft, parachute silk, portable heating unit, box of matches, 20 liters of water, 15 meters of nylon rope, 2 45-kilogram tanks of oxygen, first aid kit, solar-powered FM transmitter and receiver, and a food concentrate. So those are the 15 items, and you have to organize those 15 items and you have to rank them. So each team will be giving a rank, and then they'll be doing a total of the rank. And I have the final answers with me, so if you do the activity, I'll share those final answers with you eventually.
So this activity is one that's probably not unfamiliar to some classrooms, in that I've seen this one done on Earth, but I think the answers come up quite a bit differently when you're doing this activity stranded on the Moon than if you're stranded in Alaska or some part of northern Canada.
Right.
And the details for this activity are available on the Junior Astronaut website. Is that right?
Yes, the details are available on there.
Okay.
So you register, if you're a registered member, you'll have the access for those, for the activity.
Okay. So I would imagine the classrooms have had a chance to take a look at these now, maybe have some ideas of what they would want. Maybe we can take a look at what the answers are.
So the first item out of all those, which is ranked of highest priority, would be 245-kilogram tanks of oxygen. Because it's the most important survival need. You would need oxygen to survive. And because they have to travel for 50 kilometers, so they have to make sure that they have that oxygen tanks with them. And besides, they don't have to carry the oxygen tanks, or they're just 2 tanks, and not just that one person has to carry, so they can divide it, and it's a part of a teamwork that they can divide it among themselves, and somebody could carry something else. So 245-kilogram tanks of oxygen, the most important ones. The second one would be the 20 liters of water. Again, the water is important, and there would be, because we'll be traveling for 50 kilometers, there would be enough loss of water. So we need to stay hydrated so that we can walk through it. So, so the second priority would be 20 liters of water. The third one would be the stellar map. So because it would be a kind of a serve as a navigation for us, because the stars will look the same as they look on the Earth, so they'll look the same on the moon. So and they'll have something to navigate to their outpost, which is 5 kilometers away. So that would be the third list, the third thing on their priority list. The fourth one would be the food concentrate. It would be a very effective way of us giving them the energy, and they wouldn't have to, because they need, of course, energy all the time, and because it's a concentrated food, it will be densely packed, and it wouldn't be too much of a weight to carry. So that would be our fourth number on the priority list. And I just wanted to mention that they're kind of the same on the Earth as these conditions, because we have to fulfill our needs for the energy or the oxygen for survival. Those should be higher on the priority list as we go into, if we run into such emergency conditions. So the fifth one would be the solar powered FM receiver and transmitter. And that's because we need to transmit the signals, so that if they are closer to the outpost, so they can send signals to each other that we are getting closer, and that will be a way to communicate. So that will be number 5. Number 6 would be a 15 meters of nylon rope. That would be because of the, if somebody gets injured on the way, they can just they can tie that and pull the person up, because again, it's a matter of a teamwork, and everyone has to move to that outpost. So if some injury happens, so they can use that rope, or if they encounter a crater or something, they can do some measurement on their way as well. So 15 meters of nylon rope would be on number 6. Number 7 would be the first aid kit. Again, that's important if somebody gets hurt, because it's a long journey. If somebody gets hurt during that, so first aid kit would be very useful. Number 8 would be a parachute silk. So they wouldn't need parachute necessarily for flight purposes, but the material would protect them from the solar rays. Now on Earth, we are protected by the ozone layer in the atmosphere, but there in the space, there would be no ozone layer on the moon, and they would need a protection. So parachute silk, the material would provide a protection there. So that will be Number 8. Number 9 would be the self-inflating life raft. That will be just giving them some propulsion because they wouldn't have to take the steps themselves. So it'll give them some, it'll relieve them of some effort that they'll have to put in walking. Number 10 would be signal flares, which is, again, because of the giving, if they do not have a transmitter or receiver, they can send the signals that they have arrived the lunar post, but it's slightly lower on the priority as compared to the transmitter and the receiver because they're already communicating using the transmitter and receiver, so they can, that's ranked a little lower on the priority list. Number 11 would be the fire extinguisher. It's again because if there's no oxygen necessarily on the moon, so in the atmosphere of the moon, so there wouldn't be much fire, but these but it can be used again to give some propulsion and to relieve them of some effort there. So that's the number 12, sorry, number 11. Number 12 would be the 1 case of dehydrated milk. Again, that's a food, but that's ranked lower because we already have food concentrate very up on our priority list. So we have to trade off some things. So they traded off the dehydrated milk there. So that's number 12 there. Number 13 would be the portable heating unit. That's because they already will be in their space suits. So, and besides they're on, they wouldn't need that much of the heating while on their journey from the where they landed to the outpost. So that's number 13. Number 14 would be a magnetic compass. That's because the moon does not have a magnetic field in the same way as on the Earth. So on Earth, we can use the magnetic compass to navigate, but on the moon, it wouldn't be very useful. So it's ranked very lower, number 14. And last one would be the box of matches. And that's because it's completely useless because the atmosphere of the moon doesn't have enough oxygen or to begin with, so they wouldn't need box of matches. So that's where, so they traded off few things, such food, some food items were ranked lower, some were higher. So that's a trade-off that they had to do. And those were the rankings that were the best rankings currently.
Excellent. I'm just going to stop your screen share, and we're pretty much at the end of our time. Thank you for going through the activity. Thank you for talking about your research and cosmic carbon and all the interesting things that are filling up what we think is just empty space. To our classrooms watching, thank you for your time and attention. The next Junior Astronaut presentation will be next week on Tuesday. There will be a promotional email out for classrooms later tonight, probably see it tomorrow morning. Again, thank you to the classrooms and thank you to you, Amik.